So in previous lecture we are learn about the features importance. So we are using here features important, how the features is important and for our weight vectors. Okay, we have seen already it. Now in this lecture we are learn about the model interpretability and collinearity of these features. Okay, so first consider the model interpretability. So how the features features importance is interpretable to the model in the logistic regressions. So let's take first our query point, one query point. So let's take a query point is xq. Xq is one query point. Sorry. So in query point we have two classes, or in this query point we have either it will be +1 or positive plus, or either it will be -1, that is negative plus. Okay, just if you remember the previous class, then here we have at the end of this lecture we are taking an example for predict the gender of a human, that is he is a male or she is a female, simple. And we are using two features, one is our hair length and another one is height. At the end of this lecture we have seen that a hair length is more important to predict our gender, because if we see that its distributions are less overlapping than our height distribution of the height. So from this we are predict that in these classes positive classes, our top features is top features. If we see these positive classes, our top features is what? This hair length or hair length and height. Hair length is less important features and height is most important. Just height is the best features for the positive classes. But if we see the negative classes, that is female classes, in another language we call it, these classes is the male classes and these classes is the female classes. If we consider the female classes, in these classes the top features, which one? Top features in these cases, the top features is the hair length. Hair length is the most one and height is the less one. So from these features we can conclude that our model we can predict our interpreted if we see the features, then we can interpret our model clearly. So features importance here, features importance is most important for model interpretable, okay, in the logistic regressions. Now I think this is clear, model interpretable. Now let's come to our another concept, collinearity of this feature. Okay, so at short, features important, I write down these features important as fi features. So we see that our features when we are using our features important, we are using our features important by calculating the absolute value of the weight vectors. When it will, because we are assuming that our features are what? Our features are linear independent, simply independence. When we are assuming that our features are independent, then we can find the absolute value of W, and according to that we are decided which features which important, more important. But it is the absolute value, that is W, or we can simply that, or Wj for features I, we can simply it's calculate is absolute value when our features are independent. But the one main problem is that collinearity. So now come to the collinearity concept. What is collinearity? So this is the main problem. But Wj, it is not as suitable when our model are collinear. Suppose let's take in our model we have two features, wi bar and wj bar. Let's take and such that these two features as we have chosen these two features for a model such that one feature is dependent with another. Means what? Means one feature is linearly written by the another one. If our lambda and beta are constant, means what? If alpha and beta are constant, if we choose two constant alpha and beta, then one features is written by the another features through this linear form. Using these linear equations, we can predict one feature by the another one. This concept is called that the both are collinear. Then we can call that fi and fj are collinear. Okay, then we can call that both are collinear. Now from this, if we simply extend this concept, then we can simply find the multicollinear concept. Okay, what is multicollinear? Multicollinearity. Okay, multicollinear is a one kind of linearity, but just simple extend this. Suppose if our model have suppose four features, if there have four features f1, f2, f3 and f4, such that one features is generated by the other features. Means one features is written by the collinear form using the others one. That is, if our alpha 1, alpha 2, alpha 3 and alpha 4 are constant, then f1 is written in such a way that f1 is equals to alpha 1 plus alpha 2 into alpha 2 plus alpha f2 alpha 3 plus f3 and alpha 4 plus f4. Okay, then our features are said to be multicollinear. If these features are written as this way, then f1, f2, f3 and f4 are said to be multicollinear. Okay, now the main question is that why does wj, absolute value of the w, is not useful as our features are is not linearly independent. Means what? If it is not linearly independent, means it is collinear. Features are collinear. Now the main question is that why does this absolute value of our weight vector is not useful? Is not useful as features independent. Is not useful as features independence if our features are collinear. Now what is the problem? Now it will be clear, I think, if we discuss this concept through an example. Let's take our training set. Let's take we have a training sets that have n number of points. This is our training set where I is equals to 1 to n, and there have three features, and our optimal w is equals to w1 W star, that is 1 2 3. Okay, so this is for features 1. Let there have 3 features. Let's there are 3 features, f1, f2, f3. Okay, so w1, w2, w3, and our query point is xq1, xq2, because of we have 3 features, and so our query point, our data point as well as query point also belongs to rq. Let's take and this is responsible for response for f1 features, f2 features, and this is for f3 features. Okay, now if we want to calculate the multiplications of w star simply w star simply wq, then what will be the value? Then we first compare, we are multiplying these two, again we are multiplying these two, and again we are multiplying these two, and at the end of the day we are summed it. Just we are know what is the dot product. So dot product will be xq1 plus 2 into xq2 plus 3 into xq3. This will be our dot product. Now let's take thing why our absolute value of our weight vector is not important. Let's take our f2 features is collinear with our f1 features, mean f2 features is represented by 1.5. so let's take f1 5 into f1. Okay, let's take means f1 and f2, these features are collinear with each other, are collinear. Okay, now what will be our w transpose code? If this is collinear, then we are writing these equations xq1 as xq1, now 2 into xq2. Now we can write xq2 as this, because xq2 is responsible for what? For features 2, and features 2 is written by 1.5 into features 1. Then we can similarly we can write it at 1.5 into xq plus xq3. Simple, we can write it. If you multiply 3xq1 and 1xq1, that is 4xq1 plus 3xq3. Okay, so this will be what? So here w star will be, we can see that 403. Here w, we calculate here w. Now if we consider the two w's, w star, or we have taken w star is 1 2 3, we are taking our w star is 1 2 3, but we can find that our w star value is 403. Okay, this is the same thing. Actually at the end of the day, if you given these two weight vector, the end of the day, if you given the two weight vector, but two vectors mean what? This is the same classifier. These both are the same classifier. Okay, but they have two different weight vectors. So if you see this weight vector, that is w star, or if you take the absolute value of the wj's, then you can see these vectors are more important. Okay, this, that is f3 is the most important vector. And if you see this vector, then here you can conclude that our F1 is most important features. And F2 is not all important. F2 is not at all important. Okay, simply if you see these two vectors W star and W tilde, then you can see that at F3 is most important features in W star, and in W tilde you can see that our F1 is most important features, but these two are responsible for same classifier. Okay, so in such key situations there is a confusion occur. We are confused. So first we have to check to have taken the absolute value of a features important. First we have to check the collinearity. If our features are collinear, then we cannot use the absolute value of Wj. So write down it clearly. If our features are collinear, then what? Then weight vector can change arbitrarily. You can see here F1 and F2 are collinear. Then we have taken the weight vector 1, 2, 3, but at the end of the calculation we got our weight vector really 4, 0, 3. So our weight vector changes arbitrarily. Wait. Okay, so in this case absolute value of Wj for our features i's, Wj's cannot be used as feature importance. Okay, so to use, now conclusion is that to use absolute value of Wj's as features important, first we determine the features are multi-collinear or not. To use as a feature importance, first we have to determine if features are multi-collinear or not. If it is multi-collinear, then we cannot use norm of Wj's. If it is linearly simply independent or is not multi-collinear, then we can use it. Now to avoid this thing, there have one technique. This is called the perturbation technique. What is this? Is simply called perturbation technique. Okay. Perturbation technique. Okay. So now let's discuss what is the perturbation technique. So first let's consider we have a data like this. here suppose let's take here we have d features f1 f2 f3 dot fj ft. We have d features and we have one data point xi, and here is our output. Sorry, actually this is our y, and corresponding to yi, our y is equals to yi. Okay. And let's take for ith data point and corresponding to jth features, our data value is ij. So what happened? So first pick up h xij's. First take on the x xij's and simple increase a small value that is called epsilon. Sorry, epsilon. Simply increase this value to a small number that is called epsilon. This number is another language, if we call it, this is called a small noise. Just add a small noise in this point xij. So how to choose this small noise? Simple, we are using here the normal distribution with mean 0 and its standard deviation is small number. Suppose let's take, we are using here the small number 0.1919. Okay, yeah, 10, let's take 10, a small noise. Here it is our 0 our mean and it is our standard deviations. Using this kind of normal distributions, we are choosing our simply epsilon. Add our data points. Okay, now what? Now how we have adding this data point, but before perturbations we have to check one thing. So we have already a w weight vector, we have already, let's take this w1 w2 wj wd. Suppose this is our weight vector. Okay, this weight vector is for what? This weight vector is for before perturbation. What is the spelling of perturbation? Okay, now after perturbations, after perturbations, let's take our weight vector is w tilde, w1 tilde, w2 tilde, wj tilde, wd tilde. This one is for what? This is after perturbation. This one will come. So before perturbations we find that w. Okay, after perturbations we find this w. If we see that wi's and wj's means these two numbers, means these two ones differ significantly, then we can conclude that our features are collinear. If it is similar, both are similar means approximately equal, then we can conclude that our features is not collinear, it is independent. Let's write down the concept. If we see that if wi, sorry, here we have taken wj, if wj and wj tilde, when I after using this technique, perturbation technique means what? If you use the small noise using this distribution to our data sets, to our data sets, then if we using this perturbation technique and we got this w tilde vector, if wj and wj tilde vectors differ significantly, then we can conclude that we can conclude what? We can conclude our features vector are collinear. Okay, then we can easily conclude that our features are collinear. Means what? Means simply language, if we generate, we cannot use w mod wj's as features importance. We cannot use our nominee as features important. Okay, so I think the perturbation technique are clear, all of you. So what we are, if we see that our features are independent, then simply in linear regressions we calculated the wj's for jth features, absolute value. We are computing the jth features for wj's, norm of wj's for jth features for jth features. Okay, and the maximum according to the maximum values, we are deciding our features important. Now you will see that if our features are linearly collinear, means one feature is written and using the one features is written using the other features by a linear equations, then we can see that these features are collinear. Then if our features are collinear, then first we check using the perturbation technique. Then if collinear, then we cannot use the mod wj's as our features importance. Then first we have to check, to avoid this problem, first we have to check the both features are linearly independent or not. To check this, here we are learn that we are using here perturbation technique, this technique. Here we see perturbation technique. So how we are using perturbation technique? So first we are pick our data points. So to our data points we are using small noise, it means small values. How we choose those values? We are choosing the values using a normal distributions, using mean 0 and a small deviation, small standard deviations, that is you can as you choose a small deviation number. To these distributions we are using a small noise to our data sets. So before perturbations and after perturbations, if we see that our weight vectors not differ significantly, then we can conclude that if our weight vectors are differ significantly, then we can conclude that our features vector are collinear. If it is not differ significantly, means these both are approximately equal, then we can conclude that our features are independent. Okay, if our features are independent, then you can usually use our norm ofwij's vector as our features importance. Otherwise it will be not work here. So if it is not here in KNN, we are see that forward feature selections. So if it is not conclude that w or norm of wj's are features important, then we can simply use as KNN forward feature selection method. So if wj are not features important, then we can use as KNN k nearest neighbor. As knn we can use for what? Feature selection. Technique. Okay, I think all are about clear this concept. So if you have any problem, comment below. I will always here to reply it. Thank you.